Hi, welcome to online tutorial videos from JCBRO Labs. For more information and to download the source code of this video, you can visit us at www.jcbrolabs.org. We also provide online tuitions and help in assignments related to Matlab, Labview, and Python and other engineering related subjects. We also do freelance projects on these specified areas. So if you have any such requirement, you can contact us through our website, which is www.jcbrolabs.org. In this video, we will learn how to do a spectrum analysis. That means how to calculate the magnitude spectrum and phase spectrum from the FFT of a signal, and how to do particular in Python. So as you know, we are using the Anaconda, and from the Anaconda we are using this spider distribution to write our Python codes. Okay, so the modules which will be required for this analysis is SciPy. So the SciPy is directly available in this spider, and so you don't have to install any other new thing. But if you are not using this Anaconda distribution and using Python IDLE 3 or IDLE 2, then you have to install the SciPy module by typing the command pip install SciPy. Okay, so assuming SciPy, NumPy and Matplotlib library are pre-installed on your system. So let's start it. First, let's give a description of it. This. Okay, so let's first save it on, let's say, desktop. So we'll save it by name Signal FFT. Okay, so okay, let's start importing the required modules. So first we'll import Matplotlib library, lib.pyplot as plt, because this will be required for plotting several waveforms. Then we will be importing SciPy from scipy.fft package pack import fft, and then we'll import NumPy, because we will be requiring NumPy arrays to do certain operations as np, and then from math import pi, because we will be generating some sine waves. Okay, first let's close all the open figures. So in order to demonstrate the FFT application, how to calculate the spectrum, first we will generate a signal, and because all know the spectrum of sine wave, so to make it more convenient, we will generating a spectrum of a sine wave. So generate sine wave. So as you are aware, when we're dealing with the signal, sampling frequency plays a critical role in it. So let's first define the sampling frequency. Let's say 1000 Hertz. Now let's create a time axis. So that will be simple, np.arrange. So this is a function which generates a number from 0 to a specified limit at an interval specified. Okay, so we'll be generating a signal frequency of 1 Hertz up to 1 minute duration. So 0 to 1, and difference, so we can say the sample period, time period between two samples will be 1 by fs. So that's easy. Now let's create a signal frequency. Let's say we are generating a signal frequency of 20 Hertz. Okay, and now let's generate a signal. So let's say we are generating by x, so np.sine 2 pi f into then t. Okay, it's simple. And let's make a subplot, plt.subplot and make it 2 comma 1 comma 1. Okay, so now let's plt dot plot t comma x and make it a title. Sinusoidal signal, and we can make it a plt dot x label as time, which is in seconds, and we can make plt dot y label as an amplitude. Okay, so let's check it whether we are going right or not. Yeah, so it is a 20 Hz signal for 1 minute of duration. Okay, but title is not there. Okay, there is an error, plt dot title. A sinusoidal signal is there. Now compute the spectrum. We will compute FFT. So FFT is simple. There is a command, so we'll be using capital X. It is simple, FFT of X. That's it. So this is how we can compute it, and let's plot it on the different subplot. But as usual, and you are thinking right, it will be a double-sided spectrum. plt dot plot, and we'll be plotting the absolute value of x, because this x contains this x is a complex quantity. Okay, so it will be having magnitude and phase, so we will be dealing with the magnitude spectrum only. So that is why we are taking the absolute value of it. Okay, so let's have a look. Yeah, as usual, it is fine. We are getting two spikes, one for because it is going from -0 to 2 pi, so it is repeating at an interval of pi. So if you are familiar with the basic concepts of DSP, you will understand it. So now we want to generate, or we want to plot only half of the spectrum, because all the spectral information contains up to the half of it. So for that we need to generate the frequency axis. Okay, so for generating the frequency axis, first of all we will calculate the number, like how many numbers are there in this time step. Okay, so that we can create exact frequency axis. Generate frequency axis, because this is important. Only then we will be able to demonstrate in figure, we will be able to show in the figure like which frequency component are present in which amount. Now let's create FR, and I will be using line space that will go from 0 to 1 comma n/2, and because it is going between 0 to 1, but our sampling frequency was 1000 Hz, so this numbers frequency axis should go up to 500 Hz. That means half of the sampling frequency. So that is why we'll multiply it by fs divided by 2. So if you didn't understand it, our frequency axis will go from 0 Hz to 500 Hz as per sampling theorem. Okay, so we are making it 500, and then we are generating equally spaced samples from this line space command between 0 to 1 at an interval of n/2, which was this size of the interval at an interval of 1/500, right? And then this is our frequency axis, and we need to and because it is already, we are generating the half length of the axis in order to get the half of the spectrum. So we'll put this command afterwards of it. Okay, now once this axis FFT has been calculated, we will extract only half portion of it. half of the length, because this complete axis contains the double-sided spectrum, and we are only interested in half of it. So we'll get let's create a separate variable x underscore m representing the magnitude equals to, and we also want to normalize it. So normalization is very simple, 2 by n. Okay, we'll show the effect of this normalization afterwards. And then x, it should go from 0 to 0 to n by 2, and all these values we need to take the absolute values of it. Okay, so now let's plot fr comma, now no need for absolute value, capital X underscore m. So let's plot it. Okay, so slice index must be integer or name. Okay, that will be np dot size, because this n by 2 may not be an integer number, so we should take up to the length of the fr only. Yep. So this is fine. We are getting only one spike, and this is roughly around 20 Hertz only. We can expand it. Okay, so now if you look at carefully, its magnitude is going up to 500, while our signal amplitude, original signal amplitude was 1 only. So we in order to demonstrate the magnitude spectrum more appropriately, we need to normalize the spectrum, and that can be done simply by, because if you have gone through basics of the FFT, you will find this particular variable there, 2 divided by the length of the sequence. We have to divide. Okay, so let's run it. Yeah, now the maximum amplitude is 1, which is representing, like, this particular frequency component has a magnitude of 1 in this signal. So all our theoretical concepts are being verified in this. Okay, so now let's make it a little clear. Let's make a title of it, plt dot title, magnitude spectrum, and then we can make a plt dot x label as frequency, and that too in hertz, and then plt dot y label as magnitude. Okay, and then we need to do one more thing, plt dot tight layout, so that axes don't overlap to each other. Okay, so let's run it. Yeah, it's fine, it's magnitude spectrum. Now let's verify it. Let's take more than one frequency component. Okay, and prior to that, our signal frequency, sampling frequency up to 100 Hertz will be sufficient, because we are only plotting a 20 Hertz signal. So let's plot it again. Yeah, we are getting a 20 Hertz signal. And then we can do one more thing. We can have different frequencies. Right now it is 20 Hertz. Let's put some other frequencies, other frequency signal in the same. Okay, let's say sine 2 pi into or a 30 Hertz signal. Okay, 40 Hertz signal, but for that we need to enhance it. Let's make sampling frequency up to 300, 14 to t plus, let's have one more frequency component, 1.5 into np dot sine 2 into pi into, let's say we have a 5 Hertz of signal into t. Okay, so now we have 3 component present in our signal and we want to plot the spectrum. So as usual we should get 3 peaks at 40 Hz, 20 Hz and 5 Hz, because our third signal is of 5 Hz only, and corresponding amplitude should be there. Okay, let's run it. Yep. So this is a 5 Hz signal with an amplitude of 1.5, 20 Hz signal amplitude of 1, and a 40 Hz signal with an amplitude of 0.5. And this is how this signal looks like in time domain, and this is its frequency spectrum. So I hope you got a feeling or you understand how to do a spectrum analysis in Python, and specifically how to interpret the different frequency component from the magnitude spectrum. So if you have any doubt or any suggestion, then you can let us know by commenting below this video. So that's it for this video. Thank you.